Bom dia a todos. Vamos começar. Bom, vamos. So, again, remember X projective variety over complex numbers, and then we assume that it is smooth. And something that we started to do, we defined a kind of not traditional way of introducing the Rham cohomology. So HXC, we will soon replace complex numbers with an arbitrary field of characteristics 0, but so it was the hypercohomology M, the variety X induced equipped with the Zariski topology, and then there was this complex of differential forms. And then omega M XC and going on. And at the end of the day, we are interested to compute things with this definition. So one thing very important in this course is that we need to describe its elements. Usually in the categorical definition, you don't find too much description of elements, but let's so what we take U consisting of a cover open set UI, let's say a cyclic covering of X. What this means? This means that all the cohomologies, let's say UI1 intersected with UI2, blah, 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 UIK, and all the shifts. You can take arbitrary shift of abelian groups, but let's focus on our main example. That is XC G equal to 0. So let's say so this is so for all I bigger than equal to 1, and actually what we said, when this happens, we can use just this covering for the definition of hypercohomology. But let's, before proceeding further, let me remember, if all UI1, UI2, all these intersections UIK are affine varieties, then this is then what is stated here. It is actually Serre theorem. Serre's theorem. And well, so Serre's theorem says that let me the affine varieties and actually any coherent shift, then you don't have any non-trivial cohomology. So so the moral of the story is that we can use this this covering in order to compute with the to obtain elements of the algebraic Rham cohomology. So let me write also. So it is important in this course that we are able to write down element explicitly, because we are interested in computations also. So maybe so actually then omega is a omega 0 plus omega 1 plus omega m. And if I want to write in a better way such that people can memorize it, we had a diagram. Omega dudu, omega m. Maybe I have, maybe I just show the diagram of the previous. Or maybe it is better. It is better that I put it in. Anyway, I share part of the book. Anyway, let me first a little bit write, and then I tell what we have. So remember that we had a double complex, and the elements of the de Rham cohomology, algebraic de Rham cohomology, were in the anti-diagonal. So omega 0 and omega I is just a collection. Is just a collection of omega I. Let me just put here J, because there will be some. Okay, J, I0, I1, I m minus J, and omega J, I0 until I minus J. They are what? They are differential G forms in the intersection of UI0, UI1, UM minus J. So maybe one very important thing is that classical de Rham cohomology by C infinity forms, you have just M forms. But in algebraic de Rham cohomology, you have, first of all, you have a bunch of differential forms defined in the intersections of this UIs. You have 0 form, you have 1 form, you have 2 form, you have M forms. And at the end of the day, the D of this guy, the D of this guy must be 0. Let me show some computation in the text. So so this is part of my book with Roberto. I am sharing the wrong again. Turn. Just a moment. Present window. Okay. So as you see, so an element, as I said, an element of the de Rham cohomology. So here in the text, you see that I have written the language of abelian sheaves, but all these Sj will be, in our example, are the sheaf of differential J forms. And that then this is the algebraic de Rham cohomology. So an element in algebraic de Rham cohomology consists of omega 0, omega 1, omega m. Then each omega I is a bunch of combinatorial data. So in order to keep in mind that, so the upper index is the differential G form. This is J of differential G form, and lower indexes are the indices of open sets. And so we must have a d omega equal to 0. So d omega equal to 0. When we write down explicitly the definition, it will turn out we have a bunch of equalities. So first of all, delta omega equal to omega 0 equal to 0, and delta omega 1 is the d with this sign. And now, and the reason is that in a minute I will write in the paper. So you see that the exactness will be a bunch of identities involving a delta and the differential, delta of the check homology and d of the differential forms. And in the same way, element is defined modulo something, because we always quotient by something. And something is d capital exact. And if this bunch of equations happens, so during the course, I will do examples of curves, computing algebraic the Rham cohomology of curves. So soon we will back to all these strange equalities and so on, and we will get familiar with these equalities. But for the moment, let me just write down in the paper why we have this one. And of course, when omega is d exact, then it must be 0 in the Rham cohomology. And to be 0 in the Rham cohomology, it means the existence of all this eta j from z to n minus 1, such that this happens. So maybe let's. Okay, maybe actually I can do it here. Just a moment. Okay, let me again write down in the paper. Okay. So the idea is that just to remember, so we have in this direction we have these, and going up are deltas. And remember that at the end, d was I always forget the correct sign. D was what? Delta plus minus 1 j d, and this j is the level of check cohomology. So this means that at the end, when you have to look, let me say, is this the level in which the check cohomology is defined? Okay, so let's say for the d equal to 0. So you see that you have to take delta. There is just one contribution of let's say just here. So delta of this guy must be 0. But here to get 0, we have d of this guy and delta of this guy. So up to sign that this sign that we saw, their sum must be 0. In the same way, d of this guy plus delta of this guy, considering with this sign, must be 0, and that's why we get this with it these equalities. So anyway, this kind of this computational point of view we have to keep in mind during the course, and so this is element of the Rham cohomology. Any question? Okay, so it is slowly I have to consider. So when I write this one, x over c, this means that I consider x as an algebraic variety with Zariski topology. X algebraic variety with Zariski topology. Then slowly I will need also to consider this x an analytic Anyway, this is when I consider this one the same X as complex manifold. And another thing that I needed, it is this X infinity when I consider this one as a C infinity manifold. So they are basically the same, but their structure is different. For example, here I consider just C infinity function on X and so on. Here consider complex manifold and the holomorphic functions on X, and here X with Zariski topology and just let's say regular function on X. Okay, so let me introduce this theorem. Okay. Okay, let me again try to explain this theorem in okay. So this is a kind of nice theorem to know, and okay. So remember that in all our in our main example was this X and differential forms, and so what this proposition tells us, just assume that, that there is no check cohomology of my shifts SI. In our case, differential forms, differential I form. If there are no check cohomologies, then for the covering that we have taken, such that we can compute the hypercohomology with this covering, then this hypercohomology at the end it will turn out it will be the cohomology of these global sections of SI. Now in the paper I will just try to explain this one in our main example, and in this way you will see that there will appear the classical notion of the Rham cohomology. So let's return back to the paper, and then I will tell our main example in this case. Okay, so let's take this X infinity and what omega 0 X infinity. So this omega 0 X infinity, what it is the sheaf of C infinity functions on X infinity, omega 1 X infinity, blah, 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 omega m X infinity going on. So we have the complex of C infinity differential forms over, and the proposition that I showed you at the end of they say that it's hypercohomology. Maybe let's not to write X infinity. So the hypercohomology of this one, and remember that now X infinity is equipped with let's say usual topology and not Zariski topology, the topology that we have small neighborhoods of points and so on. So this I'm going to explain this term that will be turned out to be the classical de Rham cohomology. What is the classical de Rham cohomology? It is the kernel. So we take the global differential forms. So this gamma was the notation for global sections. X infinity, the exact ones, no, the closed ones. So their D must be 0. And then this divided by the the exact one. Exact one is image gamma x infinity omega m minus 1 x infinity, again d gamma x infinity omega m x infinity. Yeah. And in the algebraic topology, we learned that this is classical de Rham cohomology using C infinity forms. So the proposition that you saw there, it is just let's say general context of this phenomena. And remember that we have let's say the assumption that omega I. Our assumption what was that? Infinity is acyclic, and acyclic. What was this? This is the same as the. Oh, there is no cohomology. There is no check cohomology. X omega I x infinity is 0 for all I 0 blah blah blah, and then g bigger than equal to 1. So let's put also infinity here. So one of the things that one usually learns in algebraic topology, that the sheaf of differential forms, C infinite differential forms, they do not have any non-trivial check cohomology. And actually this follows from partition of unity for x infinity. So so in this case, in our example, we have our assumption is satisfied. So we only want to prove that this this equality happens. So maybe yeah, maybe if I can put again this one as a kind of a exercise. So in any C infinity manifold, the sheaf of differential I forms, their cohomologies, they are all 0 for except the zeros cohomology, which are just the global section. So in our case, this is satisfied. So let's return back what we want to see. The hypercohomology of the sheaf of the complex of differential forms, C infinity differential forms, is just the classical de Rham cohomology. And this is the one, at least the first indication that our hypercohomological definition of de Rham cohomology is not really far away from the original one. So let's go to the idea of the proof of this one. And I will just make a picture for the idea of the proof, but if you want, you can read in my book with Roberto with more words and so on. So let's go. Let me make this book just a moment. Okay. So let me do some notation here before going to. So let's call this one. H M de Rham x infinity. This is the usual de Rham cohomology. So let's see. So from where to where we have a map. we have a map from here to here. So let's write down. I have a map from MHM the Rham X infinity to the hypercohomology M. Let's skip writing X infinity, and then the complex. So the bullet here means the complex. I have a map here, and and actually this is a kind of given by just taking the representative and putting the same representative. And let me explain. So remember that the elements of this guy are, we wrote it in this format. They were inside a double complex. And okay. And it turns out that this map that I am actually considering here, if I want to write in this where it is this form 0, 0, 0, and then at the end there is this omega. So omega is an M form, and it's a global M form. And what is this omega M? So then omega M, omega. So therefore, let's write down the general element. Omega M is consist of omega M I0, which belongs, they are differential form omega M x infinity of UI0. So the last piece of an element of algebra, this hypercohomology consists of differential M forms in each open sets. As I said, you have to get used to this combinatorics and so on. Okay, and okay, so what will be my map? My map will be just omega bullets going to collection of all these guys. So this means that at the end, my let's say omega M will be just a restriction of omega to all UI0. And actually, then we can easily check that this is a well-defined map. Why? We have to show that it's D0. If you take delta of this one is actually 0, because all this omega because it's the difference, but in this guy comes from global omega. So in the intersection of two open sets, its difference will be 0. And it is D, it's D also, it is 0, because omega, D omega equals to 0. So this means that at the end I have a well-defined map. And okay, if you have to again check that if here omega is D eta, then its image also it is so it will be 0 in my the Rham cohomology. And if it is d eta, this means that at the end you can define let's say this guy here before eta restricted to UI zeros, and of course bit d it goes to here, and then you have to show that its delta is 0, and its delta is 0 because again delta is a global differential form. Anyway, the map that we define here is well defined, but we have to show that it's an isomorphism. To show that F is an isomorphism. Okay, so let's try to do this one. Well, in the text I have written how look like F inverse. Anyway, And my Roberto has also changed a little bit whatever I had written. But let me try to do it in a different way. And then if this different way together with whatever written in the text might help you to understand better. Okay, so let's so I want let's say surjectivity. Maybe let's me okay, just maybe talk about surjectivity. And then the injectivity I put it as an exercise. So let's try to do. So I have element here, omega. So my element, how it look like, omega 0, omega 1, omega m. And I want to show that it is in the image of F. So let's try to do. D of this guy is 0. So remember that delta, there was delta D, and so on. So D of this guy is 0, and at this position there is just the contribution of omega 0. This means that let's say D of omega equal to 0 will imply that delta omega equal to 0, because there is no contribution at this place from other omega i's. Other omega I, they contribute here and so on. And now we use what? We use that our covering is all the shift of acyclic in the and so there is no check cohomology. This means here we use our hypothesis. So omega must be some delta eta. So let's so this means that okay, sorry, this is omega 0 and then omega 0. And okay, let me write it in omega 0. Yeah. So this means that at the end of the day, my omega 0 comes from some eta 0 in the bottom. Okay. No. So the idea is that the element omega is defined modulo exact, D capital exact object. So I will try to modify omega in such a way that omega 0 becomes 0, and then I will make omega 1 equal to 0, and then slowly going down until reaching just to omega m, and the rest is 0, and then I will check the surjectivity. So okay, now we replace omega with let me remember the okay, maybe just plus minus, because I don't remember that that it was omega. So the idea is that I want to make a combination of this d eta 0. So d eta 0 means that at the end of the day I have element in the previous anti-diagonal. The rest are 0, and I just have 0 eta 0, and I make the d capital of eta 0, and of course omega I can add to omega whatever d of whatever element I like. So and okay, so actually here maybe again I remember the so okay, delta, okay, so that's already okay. So then actually then it will be minus. Okay, so the point is that when we do this, is still this guy in the algebraic in the hypercohomology is the same as this guy. But what happens? The point is that when we take d of this one, then the delta delta of eta 0 is omega 0. Here I will get 0, and of course omega 1 will change. This means that at the end, omega I can assume as this form: omega 0, omega 1, omega 2, omega 1, omega m. And well, I think it is already clear what we have to do. Again, the d of this guy is 0, so this means that delta of this guy is 0. And then there is a d here, something non-trivial. Again, the delta of this guy is 0, so it comes from some eta 1 downstairs. And then we modify omega with the d capital of eta 1. And we do this so many times such that at the end, my differential forms become, my element of hypercohomology becomes blah, 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 omega. There is no omega m minus 1, so there is 0, and then omega m. So this is the last step. And okay, again, I have now we claim that we have already found the elements in the classical de Rham cohomology. The d of this guy is 0. So let's say d of this guy is 0. This means that the d of this goes to 0. But the d here also is, contains delta. Delta is also 0. You see that when there is just one entry, d capital equal to 0 is the same as the d small is equal to 0 and delta equal to 0. But delta, just remember that delta omega m, and remember that what is the omega m? Omega m is the collection of differential n forms in the open set UI 0. And what is delta 0? It is just delta of this guy. It is just omega m I1 minus omega m I0 defined in UI0 intersected with UI1. So this means that this is 0. This means that I have a collection of differential form in the open set UI0 such that in the intersection they coincide. So this means that they come from the global differential form, and its d is equal to 0. So I have a global closed differential form, and this will be exactly the candidate that we were looking here. So it's well, it's a simple proof, and the same way you can verify that it is injective. And anyway, I think this kind of things I have never learned by listening somebody. Personally, I have learned just playing by myself. And I think if you want to really get familiar, you have to, for example, to try to check the injectivity. Maybe if I want to put, let's say, exercise check injectivity. Okay. Any question? Okay, so let's anyway, the moral of the story is that the hypercohomology, which is a kind of strange things containing differential 0 form, 1 form, m form, in the case of C infinity manifold, it just reduces to classical de Rham cohomology. And of course, the main property that we use, that these sheaves, they do not have any check cohomology. All the check cohomologies are 0. And this is not true in the case of algebraic varieties. That's why our algebraic de Rham cohomology at the end necessarily will contain elements who are represented by a collection of 0, 1, and m4. Okay, let me see what is the next. Okay, so let me go to this Atiyah-Hodge. Anyway, in the book I have written, together with Roberta, we have written many stuff, and that I'm trying to dribble all these things in such that in a fastest way we get into more Hodge theory argument. Okay, so let's go to Atiyah-Hodge theorem. Let me first share the screen. Okay, let's. Okay, where it is. Okay, Atiyah-Hodge theorem. Good. So this is chapter 4 of my book with Roberto. This is a kind of important theorem before the invention of hypercohomology, and it is good to carry in mind. As I said, well, in the case of affine variety, we have Serre's theorem. Well, again, I will not show it. So on the affine varieties, the sheaf of differential forms is there is no check cohomology. So if we take a affine covering of our space, then we can use it for computing the check cohomology. This we already used. As you see, it is already at the end of the last chapters of Hardt-Shorn books. Okay. Maybe I tell. Okay, there is slowly we will start using this X-ANO also, but let me remind just another theorem which is usually taught in the complex geometry course. It is called Cartan-B theorem. It's kind of Serre theorem in the context of a complex manifold. So you see the concept of Stein variety. So whatever it is Stein variety, it is just think that affine varieties, they are Stein varieties. So Stein varieties is a kind of generalization of affine varieties for in complex geometry. So they are it is a bigger class of varieties, complex manifolds actually containing affine varieties. So anyway, so this notation that you see here. So when we write X and, this means that at the end X, I consider X as complex manifold. So this means that this omega j X and is the sheaf of holomorphic differential G forms on X. Okay, so let's try to announce the Atiyah-Hodge theorem. Okay, so maybe one of the first consequences of the, let me explain this one. One of the first consequences of the of Serre's theorem in the context of affine varieties. So in the same way that I wrote right now, the hypercohomology of affine variety, the complex of differential form in affine variety will turn out to be the global sections of M forms and so on. This is the proof of this one is the same as the one that we wrote. Because what? Because we have this double complex. According to Serre theorem, there is no check cohomology. So if delta of something is 0, it is the delta of something else. So the same proof that we mentioned right now works to prove this one. So in any case, maybe it is better I just start writing, and then we will back again to. So let's say X affine variety. So again, hypercohomology. So remember that H, our complex number, H, M, the Rham, X, our complex number. It was the hypercohomology of X and the double complex and the complex of differential forms on C. And since this is affine, this will imply that by Serre, HMX, I, XC, all these check homologies are 0. And the same argument as before will imply that at the end this is kernel divided by image. So this means that global sections of omega m x c blah blah blah, and then the image of global sections of m minus 1 x c. Let me write completely. Anyway, the same proof. So it turns out that in the case of affine varieties, this hypercohomology is basically global. So this is the point. Global algebraic M forms, closed M forms, divided by global algebraic exact M forms. The difference with the previous one, previous one was C infinite forms. Here are still algebraic objects, algebraic differential forms. And so, but it's still one can ask for what is the relation with classical the Rham cohomology. So let's write maybe okay. So let's define this one as this one. So we have HM the Rham. So let's consider first X as a C infinity manifold. Consider it's a classical de Rham cohomology. And no, actually the other way. Let's first consider this algebraic de Rham cohomology, which at the end turns out to be this one. Then we have a canonical inclusion to the C infinity de Rham cohomology, because in any case, any algebraic closed M form, it's also C infinity M form, because polynomials are already C infinity functions. So we have this mapped, which is just taking the representative and putting the representative there. And so this is the one the class the algebraic de Rham cohomology, and this is the C infinity in the case of X affine. So remember that in this page our X is always affine. So Atiyah-Hodge theorem Hodge theorem says that, let's give a name. This is I think I have to. This is an isomorphism. By the way, my C-infinity de Rham cohomology is always tensored with complex numbers, and so this means that I am taking C-infinity function with complex valued. Okay. Okay, so this is the Atiyah-Hodge theorem. So let's a little bit analyze what's the content of this this theorem. This theorem in the case of affine variety cells, that let's just take, for example, surjectivity. Maybe it's just to understand there is some non-trivial statement going on. Surjectivity. What it means, surjectivity? This means that, okay, I will take omega C-infinity form and in X infinity. Then, well, it is exact, the omega equal to 0. And so this means that this omega must come from here. So what it means? There exists algebraic, M form, let's say omega tilde in X. So this means that at the end I have constructed this omega tilde just by the ring of regular function on X, and regular function on X are just constructed by polynomials. And so this means that there is this omega tilde such that that omega tilde and omega omega tilde here goes to omega here. What this means that omega tilde, when I look at a C-infinity differential form, this difference must be 0. Must be 0. What it means? It must be d eta for some C-infinity form, C-infinity m-1 form eta. So for any C-infinity m form, closed m form, there is an algebraic M form, which is also closed, d omega tilde equal to 0, such that their difference is exact. And you see that at the end it is non-trivial in the same way. What is, let's say, injectivity? Injectivity, it means that let's say I take algebraic differential form, let's say omega tilde, algebraic closed. I always write algebraic C infinity because I have many contexts, algebraic, holomorphic C infinity, so closed M form. So let's say omega tildes go to 0. Omega tilde goes to 0 here, but what is 0 here? It means that it is d of eta C infinity m-1 form. Now I have, so if an algebraic closed form is exact in the category of C infinity differential form, it must be exact in the category of algebraic form. So this means that this must imply that omega tilde is d eta tilde C infinity. Oh no, it's algebraic. Eta tilde algebraic m-1 form. And well, anyway, this means that the moral of the story is that the classical de Rham cohomology in the case of affine variety, it has always representative by algebraic objects, and more strongly we can define the C infinity de Rham cohomology just by algebraic forms. And of course, this is just true in the case of affine varieties. And unfortunately, doing Hodge theory and affine variety, we can't do Hodge theory in affine variety because this Hodge conjecture and so on makes sense for now for projective varieties. But before the invention of hypercohomology by Grothendieck, what was observed, starting from the works of Picard and integrals, was this, that at the end we just need algebraic differential form. So let me just in 10 minutes try to explain the idea of the proof of this theorem. And I think if you are interested, have a look at the proof, more details. If you have a question, write me an email, and then I can put more details in my lectures. So, but let's go to the proof in the book. Okay. Okay. So this is the Atiyah-Hodge theorem that we talked right now. And so let's try to, just a moment. So let's talk about a little bit about the proof. Okay, there are the proof I learned it from this Nora Simon's article, and actually in this article it is only called Atiyah-Hodge, and the people usually associate everything to Grothendieck, but I think I am kind of against to associating a lot of mathematics done before Grothendieck to Grothendieck. Anyway, and so the idea, the proof is taken from this article. There are some lemma coming from Voisin's book, but let's try to understand the proof. So the one step of the proof is that this big theorem of Hironaka, and it's the resolution of singularity. So this is a kind of a theorem that a lot of people, they use it, but never they go to see what is how the proof works. So all the algebraic varieties, first, of course, since they are algebraic, we can compactify it and make it a projective variety. But usually the process of projectivization will produce singular variety. And once we projectivize our affine variety, and in this case it becomes compact, we will get a singularity. So we have to desingularize this x bar, and so at the end, and actually the complement, it's called the ample normal crossing divisor of x tilde. In a moment, maybe I will write it in the paper. And then, so there is maybe again, maybe I write it in the paper. There is this GAGA principle that we are going to use, and then the idea is to reduce it to something purely complex analysis, and these two theorems will enable us to do to reduce the proof into a local complex analysis argument. Okay, I don't know, maybe 10, I'm already 1 hour. Maybe I just, okay, maybe just 5 minutes, just the beginning of the proof. And at least if you want to read the proof by yourself, you will have okay. Okay. So we have this affine variety X. So the idea then it is inside some oops, it is inside some Cn, and then at the end we can projectivize it in Pn, and then we can take its closure inside Pn. It becomes projective, but it still will have singularities, and then when desingularization. And then x bar and x bar x has normal crossing divisors. So let me just explain this one and finish the proof. So this means that at the end we get this our x, its complement will contain a lot of let's say codimension one union. Let's say this is union of codimension one subvarieties of x bar. But what is normal crossing? Anyway, if I take any point x, then in a holomorphic, so it is a holomorphic coordinate system, let's say z1, z2, z, maybe I take this one capital N, because N for me is always the dimension of Zn, so let's say N dimension of x. So there will be around let's say x such that x bar x in this there is a holomorphic coordinate system. Let's get the small neighborhood, let's call it u. In this u, so maybe let's say I have this u, I have my x, such that this guy here is just a bunch of coordinate equal to 0. z1 equal to 0, z1, z2, blah, blah, blah. Let's say zr equal to 0. Anyway, normal crossing divisor, and from the complex manifold point of view, very simple. For any points, you can have a coordinate system around this point, such that the divisor is given by just bunch of the coordinates equal to 0. And this is a kind of theorem that the people use a lot. Well, it's a Hironaka desingularization theorem. Okay, and let me. What else? The ingredient of the theorem is GAGA principle. Anyway, these things is just because you just have a let's say at least you hear the statements. If you want, you can go and see what are the proofs and so on. Serre's, okay. Serre's GAGA. What is Serre's GAGA? GAGA refers to, in French, géométrie algébrique, géométrie analytique. So maybe I, in our context, let me explain on. In our context. So first of all this desingularization and so on is algebraic, even so that the normal crossing, I defined it in a complex context. but at the end, the desingularization itself is algebraic. Okay, what is in our context? Maybe global algebraic M forms in X. Okay, first of all, algebraic M forms in X in the affine variety, since they are algebraic, this is automatic. This is actually automatic. This is not has to do with nothing to do with the GAGA automatic. These are just a global meromorphic, again algebraic meromorphic M forms with poles along let's say this X bar, the complement on X bar, X bar. So anyway, we can view algebraic M forms in X as differential forms in X with poles along X. And in the same, this is, let me say, this is a kind of automatic because polynomials, when we look them as in the projective space, they have always poles at infinity. But something which comes from GAGA, so global holomorphic M. I have to define M forms in X bar. So this is X bar is X bar projective variety. Global holomorphic. And so now I know I can use directly meromorphic M forms in X bar with poles along X bar minus X. So so once you can consider M forms on X bar with algebraic M forms on X bar with poles along this divisor, and once another time you can consider in a bigger class, apparently bigger class of M forms, holomorphic M forms with pole along X bar minus X. And the Serre's GAGA in this context says that if X bar is projective, the theorem is not valid for affine varieties. It must be projective. Well, it must be compact. And in this case, when you are talking about global sections of the corresponding sheaf, in the this category is not bigger than this category. They are actually the same. So anything's holomorphic, but considered globally of our X bar will be just algebraic. In some sense, this is a kind of generalization of this fact that if you have a, let's say, a holomorphic function on a projective variety X, then since this X is compact, this holomorphic function must be constant, and since it is constant, then it will be just again in the category of algebraic functions and polynomials. Anyway, I don't know if I will be back to the proof of Atiyah-Hodge theorem, but this is the beginning of the proof using the desingularization of Hironaka, and then using GAGAs to get this this statement. And then after that, I had plans to write the proof without this quasi-isomorphism, the language of quasi-isomorphism, just the intrinsic part of the proof. But anyway, I think I will finish here, and in the future maybe I will back to Atiyah-Hodge here. Okay. Okay.